Hello everyone, I'm Wildberger. In this video we're going to look at a famous mathematical problem which has seen a lot of interest in the last 40 years. This is the Graceful Tree Conjecture, which is perhaps the most prominent unsolved problem in the general area of mathematics called graph theory. So we're going to be discussing trees which belong to graph theory, which is generally part of the subject called combinatorics. And let's introduce this interesting problem, which is actually quite elementary and easy to state once we've made a few definitions, with the following examples. So here we have a couple of graphs, three different graphs, and I remind you that what that means is we have a bunch of vertices, in this case 3 vertices, and some edges connecting pairs of vertices. Here we have 1, 2, 3, 4, 5, 6, 7 vertices and 1, 2, 3, 4, 5, 6 edges. Here this is the Peterson graph. It's a rather famous graph in the subject. It has 5 vertices on the outside, 5 vertices on the inside, and then there are altogether 15 edges, 5 on the outside, 5 in this interior pentagram, and 5 connecting the outside pentagon to the interior pentagram. Okay, now you will notice that in each of these cases the vertices are labeled. We have assigned numbers to the vertices. So here the numbers are 0, 1, and 3. Here they are 4, 5, 0, 6, 2, 3, 1. And here, well, you can see what they are. So these are called labellings of these graphs, and these particular labellings have a very beautiful property. They have the graceful property. So what is that? Well, let's have a look what happens when we consider the differences between the labels along each edge. So for example, in this first graph here, let's have a look at this edge here joining these two vertices. There's a 0 at this end and a 1 at this end, and the difference between those two in absolute value is 1. So I'm going to put a 1 there representing the difference between the values at the two endpoints of that edge. On this edge here the difference is 2, and here the difference is 3. So we note that the edges get the numbers 1, 2, and 3 in some order. So let's have a look at this one here. The edge here between 4 and 5 would get a value of 1 because that's the difference between 4 and 5. The difference between 5 and 0, that would be a 5. Between 0 and 6 is a 6. 6 and 2 is a 4. 0 and 3 is 3. And 3 and 1 is 2. And so we see that the edges get the labels 1, 2, 3, 4, 5, and 6. All of the numbers from 1 to 6 exactly once. With this Peterson graph and the labeling that we have, let's see if we can calculate all the edge labels that are induced by this vertex labeling. So we start with labeling the vertices, and then we create from that an edge labeling by taking the differences between endpoints. Alright, so let's do this. 0, 15, the difference is 15. 0, 4, that's a 4. Here will be a 5. 2, a 3, a 14 right here, a 13 here, a 1 here. 3 and 12, that's a difference of 9. 14 and 2 is a difference of 12. Let's see, between 1 and 12, that's a difference of 11. I'll put that there. Between 14 and 4 is a difference of 10. Maybe I'll put that there. Between 1 and 8 is a difference of 7. 4 and 12 is a difference of 8. And is there any more? Yes, between 8 and 14 is a difference of 6. Let's see if we have all 15 numbers from 1 to 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So the edges all get different numbers. In fact, we get all the numbers from 1 to 15 on the edges. It seems a little bit surprising, and it's not at all obvious that we can do this, that we can create a labeling of the vertices that induces this graceful labeling of the edges. All right, so this is what we're concerned with here in this conjecture. Right, so let me introduce a few basic notions from graph theory so that we have some basic terminology to talk about this subject. So here's a graph, okay, maybe denoted G. And the essence of this graph is that it consists of two types of objects, vertices and edges. So the vertices are the blue dots, and they're labeled here, or their names are V1, V2, V3, V4, V5. So they are the set of vertices forming a set, call it capital V. And then there are also edges. So between some pairs of vertices there are edges. For example, there's an edge between V1 and V2, and that edge happens to have the name E4. So we have E4 from here to here, E3 from here to here, E1 from here to here, E2 from here to here, E5 from V2 to V5, and E6 from here to here. Notice that there's a crossing here, but that crossing doesn't represent a new vertex. Okay? Just a way of representing the relation that V4 and V3 are connected by an edge. Now in graph theory we don't concern ourselves with the actual positions on the page of the vertices and edges. So if we move the vertex around a little bit, as long as all the edge connections are maintained, we say it's the same graph. So the essential information is contained in the set of vertices and the set of edges and the relations between the vertices and edges. So we could also lay out the crucial information by drawing appropriate lines connecting vertices and edges, like I've started to do here. So what I've done is I've drawn a line from V1 and V2 to E4, representing the fact that E4 is an edge joining V1 and V2. So here are the endpoints of this edge. And I could carry on. For example, I take a look at A3, which is this one here, and its endpoints are V1 and V4. So I could draw a line from E3 to V1 and to V4. And if I did that with each one of the edges, then I would get this picture of connections between vertices and edges, and that would encode the information of the graph. Okay, so graph theory is a very big subject these days. It's seen a lot of development in the last 50 years. We're going to, in this lecture, be concerned just with basic things. So we're going to talk about simple graphs. Now these are graphs that have two properties, that at most one edge exists between any two vertices. As in this example, this is an example of a simple graph, because say between V1 and V4 there's only one edge. Sometimes in graph theory we like to consider multiple edges, like a whole bunch of roads between two cities. But with a simple graph there's at most one road between any two cities. And also the other condition for a simple graph is that there should not be any edges from a vertex to itself. There are no edges that look like this, that loop around from one vertex to itself. Those are called loops. So in other more general aspects of graph theory we talk about these kinds of things, but with simple graphs we're going to assume that there are no loops and there's at most one edge between any two vertices. Okay, so now there's some additional terms that are very common. Maybe I'll quickly go over them, not in any kind of formal way, but just to remind you or perhaps to introduce you to these words. So if we have a graph, then we might want to talk about the degree of a vertex. What is that? That's the number of edges that emanate from that vertex. So the degree of V1 is 3, because there are 1, 2, 3 edges emanating from V1, while the degree of V3 is just 1. All right, what is a walk on a graph? Well, if you think of these things as perhaps cities, and these are roads, then what a walk is a sequence. One city, one edge to a next city, another edge to a next city, another edge to a next city, another edge to the next city. So we keep on going from one vertex to another, but the vertices at each step have to be adjacent. In other words, they have to be connected by edges. So it naturally corresponds to what you might think of as a walk on the graph. And a walk is a very general thing. You're allowed to traverse edges multiple times and go through vertices multiple times. Okay, a path is a somewhat more restricted kind of walk. So it's a walk where you only go through every edge at most once. And you only go through every vertex at most once. A cycle is a lot like a path, except that the starting point and the end point are the same. So it's a walk that returns to where it started and also only passes through every edge and vertex once, except for the starting point. So an example of a cycle would be, say, start here, and then we go, say, here, and then here, here, and here. That's a path that's closed. Okay, what is a tree? A tree is a special type of graph. It's a graph that doesn't have any cycles, where you cannot make a path that returns to where you started without actually traversing an edge that you've already gone on. That's a tree. A connected graph, well, that's a graph that you can walk from any vertex to any other vertex by an appropriate walk. There's also unconnected graphs where there might be a bit of it over here and then another bit over here with no edges between those two parts of the graph. Today we're only going to be talking about connected graphs. And then a planar graph is one that can be represented on the page like this in such a way that there are no crossings of edges. So here you might say this is a little bit unsatisfactory because this edge and this edge crossed. Maybe a bit of confusion possible. Is there actually a vertex here or not? So you could redraw this graph by, imagine moving that V4 down to here somewhere. So these two edges would be just like these. And then to go from V4 to V3, we could go around this way here. If we redrew the graph, it'd be the same graph that way. We'd see that it's a planar graph. It can be represented in the plane without any overlapping edges. All right, so that's just a few very elementary notions from basic graph theory that you can easily look up in many places. So here's a good exercise for you. A basic property relating the number of vertices and the number of edges. So the exercise is that show that if you have a connected graph G, then the number of vertices is always less than or equal to 1 plus the number of edges. With equality happening, in other words, these two things are equal precisely when the graph is actually a tree. For example, here, this is a tree because there are no cycles. You can't go from any vertex back to itself with a path unless you actually go and then come back along the same edges. There are no paths that loop around coming back to where you started from. This is a tree and it has how many vertices? 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. And it has 1, 2, 3, 4, 5, 6, 7, 8 edges. So 9 is actually equal to 1 plus 8. So you might want to start by proving this for a tree. It's almost obvious for a tree. Okay, now we're going to talk about this main notion today, the notion of a labeling of a graph. So we have a graph G, and we want to define what it means to have a labeling. So labeling of G is an assignment of numbers to the vertices so that any two labels are distinct. That's all. We're just assigning numbers to the vertices so that each vertex gets a unique number. So for example, here would be a labeling of this tree. So maybe we could start by giving this one the number 0. That's allowed. And maybe this one the number 1. And this one the number 2. We don't have to use all the numbers. We're talking about natural numbers here. So maybe we could skip and label that one 4. And then this one might be 5. We might skip 6 and call this one 7. And label that one 8, 9, and 10. Okay, so that's an example of a labeling of this graph. Any two vertices get different numbers. Alright, so if we're given a labeling of a graph, we can then do something in addition. We can then label each edge, if we want to, by the absolute value of the differences between its endpoints. So this is an idea introduced by Rosa around 1967, who was basically the pioneer here, who introduced this, this notion of graceful labeling. Although he had another name for it, but it's essentially his idea. Alright, so what do we mean here? Well, if we start with a labeling of the vertices, we can then create a labeling of the edges. The same thing I was doing on the previous examples. So we take any edge, say this one here, and we label it with the difference between its endpoints. The difference in absolute value. So 4 and 7 has a difference of 3. 7 and 2, difference of 5. 7 and 5, difference of 2. Here a difference of 3. Here a difference of 5, 1, 10, and 1. Now notice that in this particular example, which I just sort of made up randomly, this is not what we're going to be calling a graceful ordering. It doesn't have the property that the previous ones did, where all these red numbers ended up being different. Here the 1 and the 1 are repeated, the 5 and the 5 are repeated, the 3 and the 3 are repeated. Okay. So this is not a graceful labeling, and that's what we wanted to get to next. This idea of when a labeling is graceful. Alright, so this definition essentially comes from Rosa in 1967, that a labeling of a graph G with, say, D edges is called graceful precisely when all the vertex labels come from the set 0, 1, 2, up to D. D is the number of edges. And furthermore, the associated edge labels take on each of the values 1, 2, up to D exactly once. So first of all, we're going to restrict the labels on the vertices that they have to come from the set 0 up to D. That previous exercise that I gave you shows that you can still manage to use those D plus 1 to label the vertices, because D plus 1 is always bigger than or equal to the number of vertices. Alright, so you can still use these labels, or a subset of them, to label the vertices uniquely. But we want that in addition to have the property that when we calculate the edge labels by taking differences, that those differences all range from 1 to D, and we get every possible number in there as a difference. So if that's the case, then we call the labeling of the graph a graceful labeling. So here are some examples of graceful labelings. This graph here, sometimes called a cycle for obvious reasons. It's a cycle with 4 vertices. And here's a labeling of the vertices, or a labeling, 0, 3, 2, 4. And that's using the numbers from 0 up to 4. Why 4? Because there are 4 edges. And when we compute the edge labels, we get these numbers 1, 2, 3, and 4. We get all the numbers from 1 to 4 exactly once. Here's another example of a graceful labeling. This is a different graph. It's the complete graph on 4 vertices, K4. That means you start with 4 vertices, and the edges are all possible edges between those 4. So in this case, there are 6 possible edges between all these 4 vertices. And here's a labeling. Assign that vertex 0, that vertex 1, that vertex 4, and that vertex 6. And that is a graceful labeling because when we look at the edges, they get labels 1, 3, 2, 5 this one, 4 here, 6 here. And after we've done that, we see that the edge labels are 1, 2, 3, 4, 5, and 6. All the numbers from 1 up to 6. This graph here, it's a lot like these ones, except there's a new vertex in the middle. This is called a wheel. Okay, a wheel is when you have a cycle that's just like this, just one after the other going all the way around, plus one more vertex right in the middle, and that interior vertex is connected to all of the vertices around the outside. So this is wheel number 5, and here is a graceful labeling, 0, 6, 4, 8, and 1. And you can check that the edge labels, well, there's a 1 appearing, a 2, 3, 4, 5, 6, 7, and 8. And you can maybe appreciate that it might not be so obvious how to get a graceful labeling. It might be a little bit tricky, especially if the graph is getting bigger. How do we assign these numbers to the vertices so that the edges get this beautiful range of values from 1 all the way up to the number of edges, each number appearing exactly once? Can we do this in general? That's a very interesting question. Can we do this for a general graph? All right, so let's make the definition that a graph G is graceful precisely when it has a graceful labeling. If there's some labeling of its vertices which is graceful. As long as we have one graceful labeling, we will call the graph graceful. And here is our famous math problem number 4. The Graceful Tree Conjecture, also called the Ringel-Kotzig conjecture. It's very short and sweet. Every tree is graceful. So that means any tree has a graceful labeling. That's the conjecture. And it's a hard problem. It gets D equals 9. Okay, so just to get you oriented, a little bit of practice. Here's an exercise. Show that the following graphs are not graceful. So here is a cycle with 5 elements. So this would be called C5. And here's sort of a bow tie graph. Here is the complete graph on 5 vertices. So we have the 5 vertices around the outside, and we have all possible edges between them. Okay, maybe that's a D equals 2 problem. Maybe it takes you a day of thinking to convince yourself that those graphs are not graceful, that there's no possible way of labeling them in a graceful way. Exercise 4.3, show that these are the only graphs that are not graceful if we restrict ourselves to graphs with 5 or fewer vertices. That might take you a little bit longer. All right, so there's maybe some generalizations. What about cycles that have more than 4 or 5 vertices? We've seen that 4 is graceful, 5 is not. So it turns out, this is an interesting exercise, that some of the cycles are graceful and some of them aren't. And maybe I won't tell you what the pattern is. I'll let you try to figure out. There's a pattern, rather nice periodic pattern with the cycle graphs. Some of them are graceful, some of them are not. What's the pattern? The pattern is also interesting here for the complete graphs. So we saw that K4 was graceful, but K5 is not. So it turns out that all higher complete graphs are not graceful. As for the generalization of these bow ties, I'm not sure how that goes. And here's another exercise for you, give you something to do. This exercise concerns very beautiful and important family of graphs called the Coxeter Dynkin diagrams. And this is just a special case of the graceful tree conjecture. These graphs are all trees. So we know, if the conjecture is true, that, that these graphs are graceful. But the exercise is to actually demonstrate that explicitly by exhibiting graceful labellings. So the Coxeter Dynkin diagrams come in two infinite families. There's the AN family, which is also called a path graph. It's just almost the simplest kind of graph. You just have a finite number of vertices all in a row, and you just connect them one by one with edges. The N represents the number of vertices. Then a slight variant on that, the DN graphs are like an AN graph, but we add one more vertex. From here we add one more vertex up, so that this vertex has degree 3 altogether, but otherwise it looks just like the AN graph. And again, N is the number of vertices. This is really only interesting if N is 4 or more. And then there are also three sort of exceptional graphs in this family. The E6 graph, the E7 graph, the E8 graph. And there they are. Now, these graphs are arguably the most important graphs in mathematics, and there's a lot of evidence for that. And we will no doubt be meeting these graphs several times in this series on famous problems, because they come up in a lot of different famous problems. So we'll meet them many times, but this is a first introduction to them, so you can get familiar with them a little bit by figuring out some graceful labellings for these trees. And we might also say that the graceful labellings don't have to at all be unique. There might be more than one. There might be many different graceful labellings. That's an additional sort of interesting problem. Can you describe all the graceful labellings, say, for the E graphs or the A and the D graphs? I don't know what those things are. Okay, so maybe this might keep you occupied for a week or so. The graceful tree conjecture has been around for 40 years, and it has seen a lot of study and attack. There have probably been dozens and maybe more than 100 papers on aspects of this question. But unfortunately, the progress has been, let's say, not as great as one might have hoped. So probably the most strongest piece of evidence that we have in favor of the conjecture is numerical computational evidence. The conjecture has been verified for all trees up to 30 vertices. So if you have a tree that has 30 vertices or less, then it has been computationally checked that that tree is graceful. And that's a fair job, because there are 14,830,871,802 different trees with 30 vertices. Exactly 30 vertices. So that's certainly some evidence, but on the other hand, 30 is not all that big. It certainly could be that there are some counterexamples for larger trees. All right, there are some theoretical results. One very nice one is this result by Hirn-Schiar and Javier in 2001, that they proved that every tree with diameter at most 5 is graceful. What does diameter mean? Well, have a look at this tree for a second. Then to go from this vertex to this vertex requires going through 1, 2, 3, 4, 5 vertices. So we could say that the distance between these two vertices is, say, 5. And the diameter is the maximum distance between any two vertices in a graph. So in other words, if any two vertices in the graph can be joined by a path of length at most 5, then we know that that tree is graceful. And then we have a whole bunch of results about particular kinds of trees. trees with very special properties. For example, we know that path graphs, the AN graphs, just strings, that they are graceful. More generally, we know that caterpillar graphs are graceful. What are they? Well, they're a little bit of a modification of a path graph. So here along the top row you see a path graph, and then underneath the path graph you have a lot of these little legs, and each leg is only of length 1, going down to a new vertex. So that's what a caterpillar graph is, and we know that caterpillar graphs are always graceful. And there are quite a lot of other kinds of trees, special kinds of trees or trees with special properties that we know they are graceful. The main reference, I suppose, for this subject, if you're interested in more information and sort of various things that have been done about it, is Jay Gallion has a survey, an online survey on, well, labellings of graphs, which includes the graceful tree business prominently. So it's an interesting problem. It's, again, a little bit of an esoteric problem. It does have some applications, but it's mostly interesting for its intrinsic beauty, really. These graceful labellings are sort of surprisingly lovely once you see them. And it's intriguing whether every tree does or does not have such a graceful labelling. I'm not at all an expert in graph theory, and I have not worked at all on this problem, but I have a sneaking suspicion that this conjecture might not be true. So my confidence level in the conjecture is not all that high. I would not bet my money on it. I give it a roughly 30% chance of being true, very, very roughly. Because I think that there's a reasonable chance that there's a counterexample, and also because we have not made a lot of sort of very general kind of progress towards this conjecture. We're still far from understanding what's really going on, which makes me think that maybe the conjecture is not true. But even finding a counterexample is a lot of work. You know that you'd have to go to a tree with more than 30 vertices, and verifying that some large tree doesn't have a graceful labelling. How are you going to do that? Because there are a lot of potentially different labellings of a big tree. So even numerically, just finding a counterexample would be very challenging. Nevertheless, if you had your heart set on tackling this problem, I might suggest to you that spend some time at least looking for a counterexample. That might be a useful thing to do. So with our next famous math problem, we're going to go back in time to the great Persian mathematician and philosopher and writer Omar Khayyam and his take on the binomial theorem. He was one of the first people to really understand what was going on with the binomial theorem. Very important problem with, of course, many, many applications, especially in the direction of modern calculus and algebra. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.